Solving exponential equations. Now, when we have an equation that's written with an unknown in the exponent, sometimes it's difficult to solve if you can't get that number it's equal to the same base. So, for example, this is written in logarithmic form. You can't type in log base 7 of 53 on your calculator. Some really fancy calculators allow for this, but most calculators only work in base 10 and base e. So given this, you can try to write it in an exponential form, 7 to the x equals 53, and we can't write 53 as 7 to a power. We know that 7 squared is 49, and 7 cubed is a lot bigger than 49, so we know that it's got to be somewhere in between 2, 7 squared, and 3, 7 to the third. So our answer is going to be somewhere in between there, and we can plug in our calculators and try to get closer and closer and more accurate. But there's another way we can solve for this. So if we take the log of both sides, the log of 7 to the x power has to equal the log of 53. Now we've done it where we've taken this and gone back over here by the property of equality of logarithms. We're just going the opposite way by taking the log of both sides. Then, by our properties of logarithms, we can say that this is the same thing as the exponent times that log. So x times log of 7 is still equal to log of 53. Log of 7 is a number, log of 53 is a number. We can divide both sides by log of 7 to isolate x, and we have x is equal to log of 53 over log of 7. Putting that into a calculator, this log is base 10 because there's no base written here, but putting that into a calculator, we get an approximate value of 2.04, which is what we expected. We could take this and substitute it back in for x to see if we get around 53. Now remember, this is an approximation, and so you might not get exactly 53. If you want to know exactly what x is, you'd have to write it as log of 53 over log of 7. Now taking this and looking back up here to our original equation, notice we took the log base 10 of 53 over the log base 10 of 7. Now this works every time. We can actually change the bases here, and we can figure out what log base 7 of 53 is. There's a formula which you can prove in much the same way we did this specific example. So if we have a log base x of y, we can write that as a log to any base we want. We can choose. Of course, we probably choose a 10 or an e because that's what we can do in our calculator. Log base b of y over log base b, that same base, of x. So we can change an unknown base that we're not able to do on our calculator to a division problem of logs with a base of our choosing, and that helps us solve equations that have that unknown base. That's called the change of base formula. So let's use that to help solve this equation right here. We could write this in logarithmic form and use the change of base. My favorite way to solve this is to take the log of both sides. And I'm going to show you some different methods on the next board, but I'm going to take you through my favorite method here. So 6 to the x equals 42. Take the log of both sides. The log of this has to equal the log of this if those two things are equal. That's the property of equality of logarithms. Using my properties, the power property of logarithms, I say that's the same as x times log of 6, and that's equal to log of 42. Then log of 6 is just a number. Divide both sides by the log of 6, and I get the approximate value of 2.09, which is what I've expected because 6 to the second power is 36, and 6 to the third power is a really big number, so I expect it to be pretty close to 2, and in between 2 and 3. So I check that, and if I check that on my calculator, I don't get quite 42 because this is an approximate value. So if I wanted the exact value, I would have to take 6 to the log 42 over the log of 6. So now, let's look at a log. This is written in log form, and I could write it in exponential form. But let's look at 3 different ways to solve this and make everything kind of come together that we've done so far. So one way I can do this, I have 16 to the x equals 64. And I see here, and this doesn't always happen, it only happens when you can write them as the same base. I happen to be able to write both of those as a base 2. Now that doesn't always happen, so this method won't always work, but in this case it will. So rewriting 16 as 2 to the 4th power, and then that's to the x power. So I just replace the 16 with 2 to the 4th, and 64 is 2 to the 6th power. And so now I have that 4 and that x. Properties of exponents say I can multiply those. So I have 2 to the 4x equals 2 to the 6th. Well, if the bases are equal, that means the exponents also have to be equal. This 4 times x has got to equal 6 if this is true. So I can just set the exponents equal to each other and solve for x. 4x equals 6, dividing both sides by 4. I have 6/4. Reducing, I have 3/2, which is 1.5. So this method only works if you can write those two numbers as the same base. The other method I could use is the change of base formula. And I'm going to use log base 10. You could use log base e if you wanted to. And I'm going to rewrite this as log of 64 over log of 16. Type that into my calculator, and I get x is equal to 1.5. Now I don't always remember the change of base formula, so oftentimes I will use this. It'll work every time, and I don't have to remember the change of base formula. So I have 16x equals 64, writing in exponential form, and then I'm taking the log of both sides. Log of 16 to the x equals log 64, and then bringing that exponent out in front by properties of logarithms. X is equal to log 16. X times log 16 is equal to log of 64. Divide both sides by log of 16, and I have log 64 over log 16, which is my answer, which is the same thing I got when I did the change of base formula, but I didn't have to remember. I could just use mathematics, and x is equal to 1.5. So you could use lots of different methods to solve. These two will work every time. This one only if you can find a same base. So now probably the most complicated problem in this section is when you have you have an unknown, but it's in both exponents. So the way I like to solve this is just to take the log of both sides. So take the log of this side and the log of this side. So log of 8 to the 2x minus 5 is equal to log of 5 to the x plus 1. And we know that's true because of the property of equality of logarithms. Take those exponents, bring them out in front by the power property of logarithms. So that's over here, and I have to put that in parentheses because it has to be this whole power times that logarithm. This one as well. This whole power times this logarithm. When I do that, log of 8, and this is base 10 because there's nothing written there, log of 8 is just a number. I could type it into my calculator and I could estimate the number. I could put the number right here, but it would be an estimate. The same is true with log 5. It's just a number. So if you treat it like a number, you should be able to do the same kind of things you would do just with a number. So in this case, I would distribute because I have x's on this side and x's on this side. So distributing log 8, I have 2x times log 8 minus 5 times log 8. So I'm just distributing that log 8. Same thing with log 5. I'm going to distribute to the x, so I have x times log 5 plus 1 times log 5, which is just log 5. So now what I want to do is I want to get my x's together. Remembering that this is a number and this is a number, I'm going to subtract x log 5 from both sides. So I have 2x log 8 minus x log 5. And here I'm going to add 5 log 8 to both sides. 5 log 8 here, 5 log 8 here, and this will make a 0 there. So I have 5 log 8 plus my original log 5 on this side. This is just a number, and right now I could estimate it as a decimal. I'm leaving it in logarithmic form to be a little more accurate. Same is true here. This is a number, and these numbers are different than each other. So it's not like you can add or you can subtract x from 2x. That number belongs to that. And so what I'm going to do in this case is I'm going to factor out an x so I can get x by itself. So factoring out an x here, I have left here, so this is the opposite of the distributive property, 2 log 8, taking out that x, minus log 5. X is on the outside there. And that's equal to this. I didn't change that at all. This is just a number. I can divide both sides by this number to isolate my x. So then I have x is equal to 5 log of 8 plus log of 5 over this, 2 log of 8 minus log of 5. Now when you're doing this on your calculator and you're doing a division problem, you will want this in parentheses before you divide this denominator. And this denominator you also want in parentheses. And the thing you're taking the log of often will show up in parentheses too. So it's really important to, when you're putting this on your calculator, remember the order of operations. And I would practice it a few times. And that's approximately equal to 4.7095. Now if you had done it in decimal form, this would be less accurate. But if you're having trouble seeing the log as a number, put it in decimal form and you can solve it just like an Algebra 1 problem.